This is Pre-Calculus Section 2.3 Notes. Today we're going to begin by talking about increasing and decreasing functions. So we're all looking at this same picture of this function y equals f of x. And if we want to talk about where the function is increasing, when we look at our picture, we're reading the function from left to right, just like we would read a book. So we would say that the function is increasing on this interval right here, and on that interval right there. So our function is increasing from n to n, and it's increasing from p to q. So as you can see, we're going to be using this interval notation to show where the function is increasing. And then we could say that our function is decreasing right here, and that is the interval n to p. So another example very similar to the last. Okay, and this one doesn't have any letters, so we're just going to use the x numbering along the coordinate plane for where we're increasing and decreasing. So this function is going to be increasing. First, I'm just going to kind of draw where it's increasing. It's increasing from here to about there, here to here, and here to here. So it looks like we are going to have a union of 3 segments. So I would say my first interval there along the x-axis here, if I'm counting, my function is increasing here to here from x is -3 to about x is -2. Oops, sorry, putting that in the wrong spot there. And the next section where it's increasing is from here to here, so that would be along the x-axis from 0 to 2. And the third interval where it's increasing is going to be from here to here, so that's going to be from x equals 3 to x equals 5. Now I kind of covered it up a little bit, but notice that that looks like it's an open circle right there on 5. So that's going to matter to us, obviously, when we write our interval notation here. We've got a closed circle at 3, but we've got an open circle at 5. So we're going to use a rounded bracket right there. And then we can take a look at where our function is decreasing. And our function is decreasing here in 2 places, from here to here. And again, note that open circle right there. So it's going to be decreasing from -2 to 0. And I'm going to put a rounded bracket on 0 because of that open circle. And then it's going to be decreasing from here to here. So decreasing from 2 to 3. Those are both closed circles on that one. Average rate of change, which you are going to see me abbreviate all the time as ARC, of y equals f of x, is the slope of the scant line AB, right here, this is the scant line AB, between x equals a and x equals b, and it's given by the equation average rate of change is equal to f of b minus f of a divided by b minus a, which, if you think about it, is the same as y2 minus y1 over x2 minus x1, but we're just putting it in terms of a function. So our next example here, we have the function f of x equals x minus 1 squared. We're supposed to determine the average rate of change of the function between the values x equals 1 and x equals 3. So first, I think it would help us if we made a little graph so that we can actually, see a picture of what this function f of x looks like. Now keep in mind our function here is in this a times x minus h squared plus k form. So we can see that that -1 inside the parentheses with the x is going to be a horizontal shift, and it's going to be 1 unit to the right. So that means that instead of my vertex being at the point 0, 0, my vertex is going to be at the point 1, 0 right here. And then otherwise, it's going to look just like a y equals x squared parabola. So I'm going to have a point here and here, and then one here, and one across from it there. Okay, so you kind of get the idea of what my parabola would look like. And again, I graphed that by using the parent function, f of x equals x squared, and then knowing that that has a horizontal shift 1 unit to the right. Certainly another way that you could do this, because really in order to find our average rate of change here, we just need to know the values of the function when x is 1 and when x is 3. So another way that we could do this is we could just make a little table of x and f of x values, and we could plug in x equals 1 and we could plug in x equals 3. When we plug them into our function, 1 minus 1 is 0 and 0 squared is 0. So f of 1 would be 0. And then when x is 3, 3 minus 1 is 2 and 2 squared is 4. So keep in mind our average rate of change formula, which we're about to do here, we're looking at the scant line between A and B on our graph, which happens to be on this picture between this point here and this point here, right? So we're finding the slope of that scant line. So it's going to be, average rate of change is going to be equal to f of 3 minus f of 1 divided by 3 minus 1. Okay, so for this problem, average rate of change is going to be equal to 4 minus 0 over 3 minus 1, which is 4 over 2. So that tells us that our average rate of change is 2. Okay, well, if we look at that dashed line that I just drew there, connecting those two values on our function, you can see that my slope here is up to right 1, up to right 1. So the slope of that scant line between point A and point B is 2. Our next situation is a little bit more of a word problem. If an object is dropped from a building, then its distance in the distance in feet it has fallen after t seconds is given by the function d of t equals 16t squared. We want to find its average speed, or again, its average rate of change over the given interval between 2 seconds and 5 seconds. So really, this is just an algebra problem. We're finding slope. Our average rate of change is going to be equal to the distance at 5 seconds minus the distance of 2 seconds over 5 minus 2, just plugging that into the average rate of change formula. Well, if we want to find d of 5, that means that we need to plug 5 into our equation for t, because we're trying to find the distance after 5 seconds. So this is going to be equal to 16 times 5 squared minus 16 times 2 squared. And then on the bottom, 5 minus 2 is 3. Okay, PEMDAS here, 5 squared comes first, is 25. 25 times 16 is 400. Minus 2 squared is 4. 4 times 16 is 64 over 3. 400 minus 64 is 336 divided by 3. So we get our answer then. Our average rate of change is 112 feet per second. The next example shows outdoor temperatures on a spring day in table format. It says find the average rate of change between the times 9 a.m. and 1 p.m. Okay? All right, so right here, if we look in the table, here's our 9 a.m. information, and here's our 1 p.m. information. And you know the rule about slope, how you can look at the ordered pairs in any order as long as you keep it consistent. So I'm going to say that my average rate of change is going to be equal to f of 1 p.m. minus f of 9 a.m. And the reason that I'm going to do it kind of backwards is because I'd like my values to stay positive. And then this is going to be over 1 p.m. minus 9 a.m. Okay? So when I start plugging things into this equation, the value of my function at 1 p.m. is the temperature at 1 p.m., which is 62 degrees, minus the temperature at 9 a.m., which is 40 degrees. And then we have to be careful here. 1 p.m. to 9 a.m., difference-wise in terms of hours, this is a difference of 4 hours. So then we end up with 62 minus 40 is 22, and 22 divided by 4 says that basically my average rate of change ends up being about positive 5.5 degrees Fahrenheit per hour. For example 4, we're supposed to find the average rate of change of f of x equals 4x plus 2 between the following points. So for the first one, we want to find between x equals 3 and x equals 7. So our average rate of change here is just going to be f of 7 minus f of 3 over 7 minus 3. Okay, well, when we plug 7 into the function, because that's what f of 7 means, 7 times 4 is 28, 28 plus 2 is 30. So f of 7 is 30 minus f of 3 would be 4 times 3 is 12, 12 plus 2 is 14. And then 7 minus 3 is 4. 30 minus 14 is 16, and 16 divided by 4 is 4. So that tells us that our average rate of change between those 2 points is 4. Now we're going to find the average rate of change between two different points on the graph, x equals negative 3 and x equals positive 2. So just a very similar calculation. We're going to do f of 2 minus f of negative 3 over 2 minus negative 3. F of 2, 4 times 2 is 8, 8 plus 2 is 10, so f of 2 is 10 minus f of negative 3. 4 times negative 3 is negative 12, negative 12 plus 2 is negative 10, and 2 minus negative 3, chop chop, that's going to be 2 plus positive 3, and here again, chop chop as well. So I end up with 20 divided by 5, which is 4. Okay. So the question here is, why did we get the same answer for number 1 and number 2 of example 4? Well, there's a really good reason for this. F of x equals 4x plus 2 is a linear function. Hopefully some of you thought about this when we were doing our calculation, which always has an average rate of change that is constant between any 2 points. Linear function means it makes a straight line, right? And a straight line always has a constant slope. Okay? The slope between any 2 points of a straight line is always the same. Finally, we have our relationship between increasing and decreasing functions and the average rate of change. So we have two different pictures here. The picture on the left side shows that f of x is increasing from p to q. Right? So then we can see here that we've got a line with a positive slope. So the slope, or the average rate of change of line PQ, is going to be a positive value. In the second picture, we show a graph that is decreasing from P to Q. And again, you can kind of see our line here. So if f of x is decreasing, or if our scant line on our function is decreasing, then the slope of the average rate of change of PQ is going to be negative. And again, that's kind of common sense, but it's good to just say it out loud and write it down.